Okay. So we want to see where would it make the most sense to put this diagram on our XY plane. Okay, so think about where would be a good, like if you were starting anywhere, where could you start on your XY plane? Yeah, you can start at 0, 0, right? Right, it's not a bad place to start. So you can put your first point here at 0, 0. All right, now if you jumped from 0, 0, where would you land? I wouldn't land at 4, 0 because the total distance that the bunny travels across is 8. Yeah, so you'd want to be at 8, 0, exactly. So this would be 8 right here. Right? So you can see how the 2 points, which are basically your x-intercepts, right? Isn't that cool? Your x-intercepts are 0, 0, which is your starting, your jumping point, and then 8, 0 is your landing point. All right, now you can see how halfway there, at 4 feet, what's the maximum height that the bunny clears? Right? Like if this was 0 and this is 8, well then halfway right here must be 4, 0, right? And then that 4, 0, you can see how well the bunny must clear those 3 feet, right? So you would go at 4, up 1, 2, 3. So check that out. You have a point right there at 4, 3. And now we draw our parabolic shape between those points. Now, what would you call 4, 3? If this is my path, sorry, I need to make that a little bit more curved out. What kind of special name? Yeah, there you go, right? This right here is our vertex, right? So it's actually pretty easy to like sketch this over, identify, hey, this is my vertex, that's the highest point, and then I have my curve. I can see my parabola there. Now, what's awesome about any parabola is that halfway between the 2 intercepts is always where the vertex will land, okay? Because you have an axis of symmetry that cuts right through the vertex here, right, halfway. So if you ever are given the information about the starting point and the landing point, but you're not given exactly like where it clears, right, where is that middle part, you just go halfway between 0 and 8, and halfway between 0 and 8 is 4. So then you know that the vertex is going to have to be somewhere along 4 on the x-axis. All right, and then that's because of the symmetry that exists in parabolas. All right, so we have a good piece of we have a lot of good information here. So what is the shape of the path of the jackrabbit? We already established that. It's going to be a parabola. Parabola or parabolic shape. Okay, and then it asks, what kind of equation would best model the situation? Well, when we're talking about parabolas, what kind of functions create parabolas? Quadratics, exactly. So what we're going to do here is we're going to bring back the general quadratic function. Okay, the quadratic function. And the quadratic function is f of x is equal to a times x minus h squared plus k. Okay, or, right, sometimes it's easier when we work with it just as y equals a times x minus h squared plus k. All right, so we know that it's parabolic, so we're going to use quadratic, so we're going to use the quadratic function in general form, okay? Because we need to then ultimately build this function by plugging in what we know about h, what we know about k, and what we know about a, all right? So that's where it takes us to part B, okay? So if you look at part B, it's asking you what point on your graph can tell you about the values of h and k in the equation, right? What do we know about h and k, and where do we find it? Yeah, check it out, right? We know that our vertex is here. Isn't the vertex h comma k? Yeah, so we know what they are already. We just have to plug it in. So then you start over with your quadratic, right? So you say y equals a times x minus h squared plus k. You know k is 3, so that's going to be plus 3. You know h is 4, so then you're going to have a times x minus. You're only replacing h, okay? So since h is 4, it's just going to be x minus 4, quantity squared, okay? You still have y equals. Exactly, that's what h and k is, right? So the vertex is h and k, all right? So it makes sense, right, that it's x minus 4 because we shifted 4 to the right. Right? You can see the vertex has shifted 4 to the right. And then up 3, so it makes sense. All right, now, what else is missing? What we have h, we have k. Yeah, we don't have a, right? We don't have a yet. Okay, so here's how we're gonna find a. All right, here's where we're gonna find a. That's the only variable left for us to find. It's okay for your function to have x and y as unknowns, right? Because that's what allows you to actually generate the graph, okay? But we need to find a, right? And that's what it's saying. Use an algebraic strategy to find the exact value of a. All right, so you've already used up one of these points. You're going to use the vertex, right, to fill in h and k. You can now use another point on the graph to help you fill in x and y, right? So x and y can be filled in with any other point on the graph. Okay, what other points do we have available to us that we can use besides the vertex? Because we've already used the vertex. I can't reuse the vertex. What else could I use? I can use an x-intercept, exactly, right? So I have two different x-intercepts. I could use 0, 0, or I could use 8, 0. Remember that a coordinate point is x comma y. This one could also be x comma y. So the one we pick does not matter. It just depends on you and your preference, right? So which point do you think we should use? Which one might give us a little bit easier of a time? 0, 0, 8, 0, doesn't matter. I'm gonna use 0, 0 because zeros are nice and easy, all right? So I'm gonna let 0 be my x, and I'm gonna let 0 be my y. And I'm gonna plug them into this quadratic that I have at the moment, all right? So I'm gonna use 0 equals a, because I still don't know what a is, times 0 minus 4 squared plus 3. Okay, so we're using the x-intercept 0, 0, okay, which is x and y, right? So that's why I've made those substitutions. Now that I've made those substitutions, I clean it up a little bit and check it out. The only variable left to solve for is a. Once I find out what a is, I'll know the entire quadratic. I won't have any missing pieces. All right, so let's clean this up. Let's solve for a. So I still have 0 is equal to a. If I clean up inside the parentheses, that's 0 minus 4, that's negative 4 squared plus 3. All right, let's clean it up now. We have negative 4 squared, so that's 16. And that's 16 times a, so that's 16a. Okay, plus 3 is equal to 0. Now I just solve for a. It's like a regular linear equation. All right, we can subtract 3 from both sides. And we'll get negative 3 is equal to 16a. All right, so if I want to solve for a, I divide both sides by 16. And a is equal to negative 3 over 16. Okay, so that's my a value, right? That's my a value. But what is the whole function now, right? What is the whole equation that represents this parabola? You would want to make sure you take a and you go back and you plug it in. All right, make sure you go back and plug it in for where a is at. So that you have a full, complete quadratic equation, right? You have your quadratic function that models the situation. Okay, so what I would get this time would be y is equal to -3/16 times x minus 4 squared plus 3, right? And then this would be the final equation that represents the parabola that we sketched out. Okay, so you can see there how x and y are allowed to be x and y. They don't need to be substituted with values. The only time we substitute in values for x and y is when we're trying to get a by itself. Okay, because we can't have 3 unknown variables. If we need to solve for a, then that needs to be the only unknown. That's why we use 0, and we used a 0 for x and 0 for y to help us solve for a. If I would have used 8 and 0, I would have got the same answer anyway. All right, it wouldn't have mattered. So the point that you pick makes no difference, as long as you pick a point that already exists on the quadratic. Okay, and it needs to be an exact point. Like, it must be for sure. Like, if you would have said, like, oh yeah, it looks like this point right here looks like it's on the quadratic, and you would have picked 2, 2, I have no idea if that point really is on the quadratic, because that's a sketch, right? You can't go based on a value from a sketch. If you know that those are your x-intercepts and those are for sure, then those are the points that you use. Do not guess trying to use another point that you think is on the graph, because that's where mistakes happen. All right, so you pick only exact points that you know of. So 0, 0, and 8, 0 are known because that's the jumping point of the rabbit and the landing spot of the rabbit. Okay, so those can be used with a guarantee that they'll help us find the a value we need. If I would have used something else, I may have got a different solution. I would have thought my a was fine, but it wasn't. Okay, now notice that a was negative. That's also good news, because look at the way the function is. It's upside down, right? It's been reflected, so it does make sense that we have a negative there. And you have 3/16, which means that's pretty wide, right? It was compressed because it's less than 1, right? So it makes sense, especially if you're kind of like jumping, right? Because you're making a wider curve. You're not making one of these like really narrow ones. All right, are there any questions about what we've done so far? Right, so although these are word problems, you have the foundation of the quadratic function. So your job is literally just complete it, right? Like, you know, h and k, most of the time all you need to do is find a, right? What is a? And then that tells you, you know, how wide, how narrow, flipped upside down or not. Okay. All right, and then finally, it says, what are the domain and range for your model? Well, it's a bunny, right? And it's jumping off the ground, and then it lands on the ground again. So the domain and range here, you're not going to have infinities, right? Because this bunny isn't jumping left and right infinitely. It's a model. We're looking at the domain and range of the model, not the equation that goes on forever, just the specific portion of this bunny jumping. So the domain, as much as I wish it was all real numbers, it's not. I have to look at how far left and how far right the graph actually goes, right? So how far left does it go and how far right does it go along the x-axis? What would the domain be? It's 8 units. I want the interval that indicates where it started and where it ended. It's an interval notation. How do I show where it jumped from and where it ended? Look at this right here. It went from 0, 0 to 8, 0. So with domain, we are only interested in the x value. So these are the 2 x values that are going to be represented in my domain, from 0 to 8. Exactly. And because we are at that point 0, 0, and we are at that point 8, 0, we can talk about them being included in the domain, right? So we're going to say that our domain goes from bracket 0 to 8 bracket, right? So it includes 0 and 8. And then for the range, similar idea, right? What's the lowest y value we have? What's the maximum y value we have, right? We're talking about a bunny jumping from the ground right? And then it lands on the ground. So it makes sense that the ground is represented by 0, right? So the y value here up to here, right? So my range only goes between 0 and 3. Yeah, from 0 to 3. Okay, we're talking about the height. So the range, we still include 0 because we can be at 0, right? The bunny is jumping from 0, and then it goes all the way up to 3, and that's the max height of the bunny's jump. Okay. So not too bad, right? We identified the path, it's parabolic. Therefore, because it's parabolic, it's a quadratic. With the quadratic, once you've already drawn your picture, you find your h and your k, and you plug those into the quadratic formula that you have. When you plug in h and k, you realize there's only one variable left to be found, which is a. You find a by using one more point. That's not the vertex. It can't be the vertex over again because then you're gonna run into problems in the calculation. So you pick another intercept point. One of them, doesn't matter which one. And you solve for a. Once you've solved for a, that's it. You just have to go back and plug it in so that you have the full quadratic equation that represents this scenario, right? And then if you're looking for your domain and your range, it's the domain and the range of the model. It's the situation that is being modeled, right? We know that the domain for a perfect quadratic, if the quadratic would have kept going forever, then yeah, we can say all real numbers, and then the range would be like -infinity up to 3. But because the bunny does not jump to -infinity, right? It's not a black hole where it just keeps falling. Then you have to limit the range, right? You limit the range and you also limit the domain because the bunny also doesn't jump from -infinity to infinity. It's not in space, right? It's not going to keep floating forever. All right. Question. We don't put nothing for a. We leave it at. What do you mean by that? A must be solved for. And when you have solved for a, you go back and you replace it. So while you're working through it, right? When we plugged in the h and the k, I was able to do that, but I still had an unknown for a. And then that's what brought me into the next part of the equation where I had to solve for a. Once I solve for a, then you must put it into your equation. That makes sense? So it's not until you found a that then you go back and replace it. But in the meantime, you'll have to keep a working through it. Okay? So I guess what you're trying to say is like, oh, if you don't see a, do you just put a 1? No, like you don't just randomly give a value. You have to solve for it. Okay, so it's a until you have found the number. Then you can plug it in as that number.